This video is meant to review part of Chapter 5 from our from the Calculus 1 course, just to give a quick overview of the way integration is interpreted and some of the ways that we approximate it, and then finally reminder about the fundamental theorem of calculus as a way of computing integrals. Much of what we do in Calculus 1 is based on what's called the area problem, which is the area between a curve in the x-axis over an interval. And what you learn there is that the way we can represent this problem is using the integration symbol. So this question would be asking, what is the integral over the integral 1, 4, over the interval 1 to 4, so here's 1, here's 4, of the square root of x dx. So that is the area problem. You would have learned in that course that if the curve had been below the x-axis, then the integral actually evaluates to be the negative of the area. And so when you have a goofy function that spends some time above the x-axis and some time below the x-axis, then you get what some people call a net area effect, where the positive areas above the x-axis are then canceled with the negative areas below the x-axis. And then what you get is not exactly a measurement of area, but it's a measurement of the difference in area between the regions above and the regions below. Anyway, so, but in the simplest case, we have a curve like this one that stays above the x-axis the whole time. And so we can legitimately use the letter A to represent the area of this shaded region. If we had no calculus at all under our belt, then one way that we could approach this would be to try to approximate the area by filling the gray region with shapes whose area formulas we do know. And so the easiest area formula that you can have that comes from rectangles, because the area of a rectangle is just based on its height. And so, for example, in the picture on the right, I have drawn 6 rectangles that lay on top of where the gray region is. And so visually, I can see that the area of these 6 rectangles, if I take the area of each of the 6 rectangles, add them together, that will be an approximation of the gray area. And I can even see that the answer is going to be a little bit too small, because I can see from the picture that my rectangles are not really fitting against the curve this way that the gray stuff does. So when I want to compute this area, the main thing is that the height of each of these rectangles is actually coming from a y-coordinate on the curve. So for example, here x equals 1, the height of this rectangle comes from the height of the curve at that point. But at this point, the height of that point is just its y-coordinate. We know that the y-coordinate above x equals 1 would be f of 1. And because we know the formula for f, we can figure out that that is actually happening at 1. I know that's not much news, because you can kind of see over here that that's what the y-coordinate is going to be. But the same reasoning can be applied to any of these points. So for example, this point right here, if I think about it a little bit, I can figure out that that's above the x-coordinate 3.5, because 3 is here, 2 is here, 1 is here, 4 is there. So the x-coordinate here is 3.5. This dot is on the curve above 3.5, so the height of that dot, in terms of how high it is above the x-axis, is f of 3.5, which is the square root of 3.5, whatever that is. But the main thing is that that's the height of that rectangle. Notice that the width of each rectangle, if I get my pen again, the width of each rectangle is 0.5. That's the width of each of these pink rectangles. And the way I've drawn it, I've split these equally, so they're all 0.5. If you take an advanced calculus class, you will learn that that doesn't really matter, that they're all exactly equal, but that is the easiest way to split them up. And the notation that you might have used in Calculus 1 would have been delta x to represent the change in x values. Those are marks along the x-axis, and so those are all x values. And so the 0.5 would be the difference between successive x values. in calculus and in math and science in general, we use this the letter delta. That's a capital Greek letter delta to represent change. So delta x would be change in x. So at any rate, the bottom line is that because we now know how to find the heights of each of these rectangles, and we know that the base or width of each rectangle is 0.5, then it's a simple matter of just writing down each of these height times width, height times width, height times width all the way through. You can see this height times width here. That's the one corresponding to the first dot that I drew. Height was 1, width was 0.5. That's the area of this rectangle. And then this last rectangle, the height we figured out was the square root of 3.5, whatever that is. And the base, again, the width was 0.5. So square root of 3.5 times 0.5 would be the area of this last rectangle. And so each of these corresponds to one of the rectangles. And in this case, it's added up to 4.41. And so not only do I know that's in the ballpark of my shaded area A, but I can see from the picture that that's actually less than A. I'll write less than A, but pretty close. Now, there's nothing magic about drawing the rectangles so that, I didn't say the why I called it that. The L here, the reason I'm using L, the 6 is obvious. I'm drawing 6 rectangles. The reason we use L is because the tops of the rectangle touch the curve on the left side. Notice how each rectangle's top is touching the curve on the left side of the rectangle. So if I can draw it with the left sides touching, obviously I could draw it with any part of the top touching, and that gives us some more things to do. I should also mention here the notation. As I said, the delta x is what we refer to as the width. Notice that these values of square root of 1, square root of 1.5, square root of 2, square root of 2.5, those are all just arrived at by plugging in the x coordinate into the formula. So if I call the function here f of x, then this is f of 1, this is f of 1.5, this is f of 2, f of 2.5, and so on. And so each of these expressions that I'm adding up is f of an x value times delta x. So if my x values are these numbers across the bottom, x1, x2, x3, x6, across the bottom, which I know is 1, 1.5, 2, 2.5, and so on, then this way of writing it is exactly the same as this way of writing it with sigmas. Being able to use a sigma to represent a sum is very important in this course. And so we will be doing some exercises where we're going back and forth between the sigma notation and the longhand early on, so that it's not too hard to look at later on when it's more important. The other thing to notice about this notation is that the theory of calculus is telling us that this is an approximation to the actual area. But remember, the actual area we said was represented this way. So notice how the notation has been invented to have everything match up as much as possible. This sigma, that means sum, has turned into this more continuous looking big skinny S. And that's not a coincidence. The person who invented this notation is a guy named Leibniz in the late 17th century, early 18th century, was thinking about this as representing a sum. That's why it looks like an S. And so it plays off of this Greek letter sigma that had been used for summation even before his time. The f of some x values looks the same, and this times delta x becomes times dx. So we can think of dx as being the limit of a process where these delta x's are made smaller and smaller and smaller. And so the dx and the delta x really are representing the same things, just one is in the continuous formula and one is in the discrete summation. Okay, so now this is what I was starting to say. If we can do this with left rectangles, we can also do it with right rectangles. If I were to fill the space using rectangles whose tops touch the curve on the right-hand side, then I would have this thing. And again, the bases are all 0.5, so delta x is 0.5 again. And every rectangle height is going to come from calculating f of a corresponding x value. So for example, this dot has as its height f of 4 because it's sitting above the x coordinate of 4. And f of 4 would be the square root of 4, which would be 2. So we know that the height of this last rectangle, this last one here, the height of this rectangle is 2, and the width is 0.5. And that would be this term here in my summation. So everything about this looks exactly the same. The heights of the rectangles are just f of the appropriate x coordinate. The widths are all delta x, all the same at 0.5. And so once again, this using sigma notation. And you'll notice it looks exactly the same as what we wrote before. But in this case, the x's would have been labeled slightly differently. So the x1 would be here, and the x6 would be here. You might have to look back at the previous slide to see how that's different than what I did before. But the form of this approximation is exactly the same, and so it makes sense that this is approximating the same area. Now you'll notice that these rectangles don't fit the curves all that well. The red rectangles were all pretty small, pretty far under the curve, and these are all sticking out pretty far. But these two estimates are not that far apart. The estimate with the pink rectangles was 4.41, and the estimate with the blue rectangles was 4.91. And I can see geometrically that the pink rectangles are smaller than they should be. They're smaller than the actual gray area. And the blue rectangles all stick up above the gray area. So I can conclude from that that the real area is somewhere in between these two things. So a good guess would be just to go halfway in between. That's not quite going to work for this to get us the exact answer, but that would be a good place to start. There's nothing magic about 6 rectangles, of course. If I were to increase the number of rectangles, here on the left I have 30 left rectangles, and on the right I have 30 right rectangles. If you look closely, you'll see the left rectangles still don't quite come up to the line. So that's obviously just a symptom of being a left rectangle, not so much about there being 6 or 30 or any particular number. So the left rectangles are going to be below the curve for sure, and the right rectangles all stick up above the curve. So the true area is definitely going to be between these two values. And if I ask a computer to calculate these values, it tells me that the left rectangles add up to 4.62 and the right rectangles add up to 4.72. So I'm getting a much more accurate idea of what the actual A should be. It's going to be somewhere in between 4.62 and 4.72 because of these two calculations. Notice that as soon as I've turned the corner here and gone from 6 rectangles to 30 rectangles, I do not want to touch this with a calculator. I really want to have a computer to do the calculations. But the area of each rectangle is still just the base times the height. The base is still just the delta x that I could calculate. And each of those heights is coming from f of the corresponding x coordinate. So the way that the rectangle areas are calculated is exactly the same. There's just more of them, so we'll let a computer do the work. Just to see how the A gets narrowed down further, let's look at the numbers for what happens if I go up to 300 rectangles or more. I won't draw the corresponding pictures to these. They get very washed out by having so many rectangles that you can't see the difference between the rectangles and the curve. But with 300 rectangles, the sum of 300 left rectangles is 4.66, and the sum of 300 right rectangles is 4.67. So again, I know my A is somewhere in between those two, and that's getting very specific. And then if I go to 3,000 with a computer, the sum of 3,000 left rectangles is 4.666, and the sum of 3,000 right rectangles is 4.667. And so my actual value of A is somewhere between 4.666 and 4.667. So now we have a very good idea of what the actual area A is here, just from being able to do approximations. Now, the other way of doing this problem that you would have learned about in Calculus 1 is to use the fundamental theorem of calculus. Again, the exact area, that I want to compute here is the integral from 1 to 4 of the square root of x dx. And we know from our approximations that should be somewhere around 4.666, somewhere between 4.666 and 4.667. So we have an idea of what this number ought to be. The fundamental theorem of calculus states that when we do an integral, we want to compute a definite integral. We can do that by just calculating f of 4 minus f of 1, and I now have realized I shouldn't have called this thing f before. So let me just if the function that I'm integrating is called f prime, then the fundamental theorem of calculus tells me how I can find the integral of this formula. So in order to do that, what we need to do is to find a function whose derivative is the thing that I'm trying to integrate. So in other words, I want to find a function whose derivative is the integrand. We call that an antiderivative of, oops. An antiderivative of the square root of x. So in this case, we can check that this function will work. If I take 2/3 x to the 3 halves and I compute its derivative, this 3 halves will drop down in front, multiply by the 2/3, and will cancel out. And then the power goes down by 1. 1 less than 3 halves is 1/2. So the power coming down front is going to cancel the 2/3, and the power going down by 1 is going to come down to 1/2. So the derivative of this thing is equal to x to the 1/2. Now there is a, that's the power rule for derivatives that is making that happen. The power rule for integration, power rule for antiderivatives, says that if I want to find an antiderivative of x to a power, then I will get something that has whose power is 1 more than the power of the integrand that I started with. But then to actually have it come out to be exactly x to the p when I take the derivative, I need to have in front of this the reciprocal of that new power. So the way I would think about this is I always leave myself some space here. I always think here about what is 1 more than the original power. So I'm going to have to add 1 to that p. And then once I figured out what this x to the p plus 1 is, then here I'm going to put the reciprocal of that power. So that's exactly what I'm doing here. If I know I want to get x to the 1/2 as my answer, I'm first adding to 1/2. I'm adding 1 to 1/2 and getting 3 halves. So I'm first figuring out what this power is going to be. And then once I know this power is 3 halves, then the number I'm going to put out front is just the reciprocal of 3 halves. So that's how I need to put the 2/3 there. The 2/3 is the reciprocal of 3 halves, but I'm figuring out this power first and then putting the reciprocal there. Again, I'm only belaboring that point because that is a place where people make a lot of common mistakes, especially when the powers of the integrand are fractional or negative. There's a tendency to mess up that rule. Anyway, but this is an antiderivative of x to the 1/2, and so the fundamental theorem of calculus says that the integral of the square root of x ought to be just the antiderivative evaluated at 4 minus the antiderivative evaluated at 1, and so I would get these two things, and I can resolve those, end up with 14/3. I'll note that 14/3 is 4 and 1/3. I'm sorry, 4 and 2/3. And that's 4.666666 repeating, and that is exactly what we saw happening with our approximations. So the problem with the fundamental theorem of calculus, of course, is that it requires that we're able to find an antiderivative. And one of the things we're going to find in this course is that sometimes finding an antiderivative is actually hard, and sometimes it's actually impossible using our regular elementary function set. So the approximations that we can make in both the ways using rectangles plus some other ways that we'll develop in this course turn out to be extremely important.